20 minutes ago, your agent was brilliant. It understood the code base. It wrote clean code. It followed every rule. Now it just re-imported a file it deleted. It's contradicting itself. And the architecture you explained, gone. You didn't do anything wrong. Your agent didn't get dumber. Something more interesting happened. It ran out of room. Here's what is actually going on. Every agent lives inside a context window. That window holds every message, every file it read, every command it ran, every line it wrote. The standard window is 200,000 tokens. In 2026, Claude Opus and Sonnet both offer a full 1,000,000 tokens on higher plans. Sounds huge. It fills faster than you think. One medium TypeScript file is roughly 2,000 tokens. Read 10 files, exchange a few messages, and you have burned 50,000 tokens without noticing. And here is the part nobody tells you. When the window hits around 83%, Claude Code triggers auto-compaction. It summarizes the conversation to make room. The summary is decent, but details slip. Instructions get paraphrased, and that is the exact moment your agent starts contradicting itself. It is not a bug, it is physics. Your agent is not forgetting because it is broken. It is forgetting because the glass is full. So the real question is not how to stop it. The question is how to engineer around it. 4 mechanisms. 1 harness loop. Let's build them. Mechanism 1. Planning. Think of planning like GPS. The route is picked up front, and when traffic hits, the GPS recalculates, but the destination never changes. Most developers think planning is a productivity thing, a nice to have. It is not. In a harness, a plan is persistent state. When the agent writes a TodoWrite list at the start, that plan lives outside the model. It survives compaction, it survives subagents, it survives the window filling up. Here is the wrong way. You type a vague goal and let the agent wander. 10 messages in, it has lost the thread. Here is the right way. You ask the agent to write a plan first. 5 steps. Each step has a success check. Then the agent executes step 1, marks it done, moves to step 2. When the context fills and a summary fires, the plan is still there, word for word. In my tests, giving an agent a written plan cut off track behavior by more than half. No new model, no bigger window. Just writing the plan to disk. Planning is not overhead. Planning is memory that does not fade. Mechanism 2. Subagents. A subagent is like hiring a specialist for one task and firing them when it is done. The main agent keeps its context clean. The subagent does the dirty work in a fresh window and reports back with only what matters. Here is the wrong way. You ask your main agent to read 40 files to find one bug. 40 files times 2,000 tokens equals 80,000 tokens burned, and most of those files had nothing to do with the bug. Now your window is polluted with noise for the rest of the session. Here is the right way. You spawn a subagent. You say, find the bug across these 40 files and return only the file and line number. The subagent reads. The subagent searches. The subagent returns 3 lines of output. Your main agent gets the answer. It never saw the noise. Anthropic's own engineering blog documents this pattern. Their internal 3-agent harness splits planning, generation, and evaluation into 3 separate context windows. Same model, different rooms. Here is the honest limit. Subagents cost extra tokens because you pay for the subwindow too. For one-off lookups, the trade is worth it. For quick questions, it is overkill. Mechanism 3. Skills. A skill is like a textbook on a shelf. It is not in the agent's head until the agent decides to open it. This is the shift nobody explains well. Before skills, you had 2 options. 1. Stuff every piece of domain knowledge into the system prompt and watch the window die on the first message. 2. Leave knowledge out and watch the agent guess. Skills fix the trade-off. Each skill is a small file with a name, a description, and a body. The agent sees only the name and description up front. That costs maybe 30 tokens. When the agent hits a task that matches, say, writing a remotion animation, it loads the full skill on demand. The body might be 2,000 tokens of rules, patterns, and examples, but you only pay for it in the moments it is needed. Here is the non-obvious insight. Skills turn your context window into a search engine. Instead of carrying everything, the agent carries an index and retrieves pages when they become relevant. Same model, same window, way more knowledge available. Mechanism 4. Compaction. Compaction is like a student taking notes in a lecture. The full lecture is gone, but the key points, the definitions, the formulas, the one example the professor hammered, those stay. Auto-compaction in Claude Code fires around 83% capacity. That is the default. But here is what most developers miss. You can call it yourself. The /compact command lets you compress on your terms right before a big task, so your window is fresh when you need it most. And you can pass a focus, /compact keep API design decisions and the current test plan. Now the summary is not generic, it is targeted. Here is the wrong assumption. People think compaction is a last resort, a safety net. It is actually an offensive tool. Power users compact deliberately between phases of work to reset the window without losing the thread. Think of it like saving a checkpoint in a game. You do not wait for death, you save before the boss fight. Here is where it all clicks. The agent receives a task. Mechanism 1 fires, a plan gets written. Mechanism 3 fires, relevant skills get loaded. The agent executes. When a subtask is heavy, Mechanism 2 fires, a subagent runs it in a fresh window. The window fills. Before it hits auto-compact, Mechanism 4 fires, you compact with a focus. The window resets. The plan is still on disk. The skill index is still attached. The loop repeats. This is not 4 separate tricks. This is one loop. The same loop every production agent runs, from Claude Code to Cursor to the harness in Anthropic's own research tools. Your agent stops forgetting, not because the model got smarter, because you engineered the memory around it. Honest limits. This harness does not make your agent smarter, it makes it more reliable. If the base model cannot reason through your problem, no amount of planning or compaction saves you. The harness also adds complexity. More mechanisms means more things to debug when something breaks, and subagents cost extra tokens because you pay for the sub-window. Use them when the signal-to-noise ratio justifies it. Not every task needs 4 mechanisms. A one-line bug fix? Skip the plan. A quick rename? Skip the subagent. Engineering is about picking the right tool at the right scale. So here is what is coming. In the next session, we add task persistence and background operations. The agent writes its plan to disk as a dependency graph. It survives a crash and resumes exactly where it left off. It runs tests and builds in the background without blocking its thinking. That is the jump from a toy agent to a production one. If this helped, hit subscribe. The whole Harness Engineering series is free, and every video builds one more mechanism. See you in the next one.